All right. All right. Well, thank you everyone for the opportunity to speak, and thank you, Jenny, for the invitation. So I'm Dr. Jesse Cordier. I'm a pediatric radiologist at the UCSF Benioff Children's Hospital, and I'm co-founder of Sierra Medical. Again, we're using augmented reality to impact pre-surgical planning, training, and education. And I'm excited to share with you a little bit of the work that we've been doing here at UCSF and at Sierra Medical. Really, I think this is a nice idea. Really, is a great quote about the ultimate test of your knowledge is the capacity to convey it to another, to be able to take that information that you have and convey that in a really meaningful way. And that really applies, I think, to what we're going to be talking about today. So I'm going to start off with a little brief definition of terms, AR, VR, what's the difference? We hear a lot of the terms, so wanted to define that a little bit. Talk about what I see as the disconnect between augmented reality or between the real world, our medical imaging, and the actual surgical applications as well. Talk about some of the applications that I see for this technology within radiology. And then finally talk about what I think are some interesting future directions specific to augmented reality. Really this idea of virtual experience is not something novel. It's actually been around for quite some time. And this is just one example, the Sensorama that was built in 1962. And as you can see, this was actually meant to be a virtual bicycle ride through Central Park. And it had sights, sounds, and if you can look closely, actually even smells, so aromas. This was meant to be a virtual experience. So this is not necessarily a novel concept. But when we talk about the definitions for these terms, we think about the virtuality continuum, and that is from one end of the spectrum, from the completely real world, real environment, to on the other end of the spectrum, the completely virtual environment. So we can think about the matrix, something where you're completely immersed in sight, smell, sound into a virtual environment. Augmented reality falls really closer toward the real environment, where we're superimposing digital information onto a real world background. Virtual reality, again, falling closer toward this spectrum. And then mixed reality being a term that really encompasses everything in between these two things. To break this down into a more dichotomous relationship, virtual reality, it's a digital environment, you're enclosed, it's a synthetic experience, whereas augmented reality, again, real world, really is the central part of the experience and it's enhanced by virtual details. So that's a little bit of the definition of the various terms. One, I just wanted to get a little bit of the disconnect of where I see that between medical imaging and surgery. So in a former life before I was a radiologist and entrepreneur, I was a surgical intern. This is me here at the University of Hawaii. And what I found and learned among many other things during that time was that the way that we plan surgeries hasn't really changed a whole lot since this picture was taken more than 50 plus years ago. Perhaps our attitude towards smoking in the reading room has changed a bit, but overall, the idea of the way that we plan really hasn't. So as one example here, I asked one of my surgical colleagues in orthopedics to show us a way that's still used to plan orthopedic surgeries, even now in 2021, which is literally printing out a digital picture of printing out this image of a radiograph using scissors, cutting it, and using Scotch tape to simulate your correction, and then having that taped onto into the OR. So again, still a method that is used to correct a deformity of the femur in this particular case. So this really got me thinking, how can we better leverage the types of technologies that we have in imaging to really give a fuller picture, a more realistic picture for our surgical colleagues? And so through work that I did initially, buying my first HoloLens, learning how to code, and creating my first application, we came up with some of these solutions here. Because really the challenge is, as a radiologist, my training is to take this stack of 2D images and make a 3D model in my head and try to then to take this information and convey this in a number of ways. But the ways that I communicate this right now is, again, in person, where I'm reviewing this with a surgeon, over the phone, where I'm again trying to verbally communicate all these complex visual spatial representations. But ultimately, it's via my report as a radiologist, dictating and putting into words and trying to paint in words a three-dimensional picture of a very complex patient with a lot of information that you just saw. And still, I found myself having to draw doodles, having to put together something so that I could show, again, trying to convey this complex information to my surgical colleagues. So looking at various solutions, the challenge is for the surgeon is that when they go into the operating room, they don't see something like this. They see this. And all the information is hidden beneath the surface. And it's very challenging for them to be able to then conceptualize all this thing. So how can I better translate the information here to them? because they end up having to, as surgeons, try to spend this time to make those models in their own mind. And it turns out the studies show they're not all that great at it. That's not their primary training. Their primary training is to how to fix and repair and how to do an operation. This translation is actually very difficult. And what that leads to is a lot of unexpected things when they're in the operating room. So the planning means a lot more troubleshooting on the fly, more time under x-rays and fluoroscopy for the surgeons, longer OR times, and even more complications. So again, what if we could then better bridge that gap, translating this information into a more accurate 3D representation? So again, there are great solutions like 3D printing that are available, though there are some considerations: time, cost, availability. Are there additional ways that we can further complement this information? So what about augmented reality? So again, I was first exposed to this through very different mediums here. And so what I'm seeing here is what we did is take this information and turn this into a true usable model. So this is something from an application, one of the first prototypes I built. We then got promising data. We were then funded by our UCSF Innovation Ventures program to then further develop this and recruit and build our team and turn this into something that actually can be used. So I'm going to next talk a little bit about some of the various applications that we've done and use this within radiology and pre-surgical planning. Through my network of collaborators, we put together really a list of all those folks who are using and applying this technology within the radiology field. And there's a lot of different ways, both in education, training, pre-surgical planning, communication, and clinical care that we can use this in. We first started wanting to test the accuracy. So if I say a model is 5 millimeters, or if there's a structure that's 5 millimeters in size, how close is that to reality? So we did accuracy and precision testing with phantoms and published this information with our collaborators at UC Berkeley. We did the same thing using MRI, and we developed along the way proprietary technology to be able to optimize those images to translate from MRI to the best holographic model. Again, published this with our collaborators in our master's program here at UCSF Radiology. And finally, we wanted to then, with that information in hand, how well can this be used for things like education, for training? And so we use this at UCSF with our medical student small groups, comparing their peer-to-peer learning with cadaveric models. And what we found was that this augmented reality applications proved just as effective in teaching and training and retention of information compared to our standard cadaveric models. We've also used this in our training for radiology technologists and helping them to find and understand the best optimal ways to get the best radiographic views the first time, therefore reducing needs for repeats. And then clinically, we've been able to look at this using our orthopedic colleagues for pre-surgical planning for fractures. So comparing the ways that they planned previously versus using these three-dimensional models. And again, they found that these were highly accurate. They would even estimated time savings up to about 21% of time in a complex elbow fracture case by our most experienced surgeons. So a lot of really exciting potential that we then published that as well. So we're really using this and see this use case in the pre-surgical planning area where we can make a lot of the important decisions first about how long to book the case, what types of hardware would you need. Here's one example where we have a 15-year-old male who had fibrous dysplasia. It's a disorder of the bone that led to fractures and this disfiguration of the bone here. And the surgeon, instead of the old way of printing and using scissors, we made a three-dimensional model for them. And they were able to, in the reading room, plan out this with this accurate method, again, three-dimensionally, and then even reconstruct this fracture and this repair, plan this repair out, and literally digitally have a version of this before walking into the operating room. And they had a great outcome. And so this is the type of application that we see both for pre-surgical planning and then further for patient education. So for enabling a patient to better understand some of their conditions and to have a better understanding of less anxiety, better consenting are some of the other applications we see. And this has led us to develop this tool, which has allowed us then to better visualize using a very simple iOS-based platform to be able to manipulate these, to design and load models from the cloud so that you can have thousands of models at your fingertips to be able to then understand, scale, resize, remove through, measure, and even annotate a model and record your session, all using a simple platform. Where we go in the future, what we're seeing is more combined models where we're taking information from MRI, CT. This is a spinal tumor. We're using diffusion tensor imaging fused with